Let's start now. Black holes. Black holes are the ultimate cosmic predators, formed when massive stars collapse under their own gravity. At their core lies a singularity, a point where density becomes infinite and the known laws of physics begin to break down. Surrounding it is the event horizon, the boundary beyond which nothing can escape, not even light. This makes black holes completely invisible. We can't see them directly, only their effects on nearby matter. Gas, dust, and even stars can be pulled in, forming an accretion disk that heats up and emits intense radiation before disappearing forever. If you were to approach a black hole, you wouldn't simply fall in. You would experience tidal forces so extreme that your body would stretch vertically while compressing horizontally, a process known as spaghettification. Every part of you would be pulled apart at the atomic level. Even time behaves differently near a black hole. To an outside observer, you would appear to slow down as you approach the event horizon. But from your perspective, everything would feel normal until the very end. Some black holes don't stay in one place. They can be ejected from galaxies and travel through space undetected, making them even more dangerous. Gamma-ray bursts. Gamma-ray bursts are the most powerful explosions ever observed in the universe. They occur when massive stars collapse into black holes or when neutron stars collide. In just a few seconds, they release more energy than our sun will produce over its entire lifetime. But what makes them especially terrifying is their directionality. Instead of exploding in all directions, gamma-ray bursts emit focused beams of radiation that travel across the universe at nearly the speed of light. If Earth were ever in the direct path of one of these beams, the consequences would be catastrophic. The atmosphere would be severely damaged, and the ozone layer could be stripped away almost instantly. Without that protection, harmful radiation from the sun would reach the surface. This would lead to rapid environmental collapse. Plants would die, food chains would break down, and mass extinction could follow in a very short time. The most frightening part is that we would have no warning. These bursts happen suddenly and travel at light speed, meaning we would only know after it had already reached us. They are rare on a cosmic scale, but the universe is vast, and even rare events happen somewhere all the time. Rogue black holes. Rogue black holes are black holes that are no longer anchored to a galaxy. They are created when gravitational interactions or violent cosmic events eject them into intergalactic space. Once free, they drift silently through the universe. Because they emit no light, they are almost impossible to detect unless they interact with something visible. Astronomers can sometimes identify them through gravitational lensing, where their gravity bends light from distant stars. But this only works in very specific conditions. Most rogue black holes remain completely invisible. That means one could be moving through our galaxy right now without us knowing. If it passed near our solar system, its gravity could disrupt planetary orbits, potentially sending planets or asteroids into unstable paths. Unlike other cosmic threats, rogue black holes offer no visual warning. There is no glow, no explosion, no signal, just a distortion of space itself. By the time we could detect its effects, it might already be influencing objects around us. This combination of invisibility, mobility, and extreme gravity makes rogue black holes one of the most unpredictable dangers in the universe. Rogue planets. Rogue planets are planets that have been ejected from their original solar systems, becoming cosmic wanderers with no star to orbit. These violent ejections can happen due to gravitational interactions with other massive planets, close encounters with passing stars, or chaotic events during the early formation of a planetary system, sending them drifting alone through the vast emptiness of space. Without a host star, these planets receive no consistent light or heat. Their surfaces quickly freeze, temperatures drop to extreme levels, and their atmospheres may collapse or become incredibly thin over time. They become cold, dark, and nearly impossible to detect with traditional observation methods. Scientists estimate that there could be billions of rogue planets in our galaxy alone. Some studies even suggest they might outnumber stars, meaning the Milky Way could be filled with these invisible, drifting worlds moving silently through interstellar space. Because they don't emit their own light, we usually detect them only when they pass in front of distant stars, briefly bending and magnifying their light through a process called gravitational microlensing. These detection windows are rare and short-lived, making rogue planets extremely difficult to track. Despite their frozen surfaces, some rogue planets might still retain internal heat generated by radioactive decay or leftover formation energy. This could allow subsurface oceans to exist beneath thick layers of ice, potentially creating isolated environments where life could survive in complete darkness. However, from our perspective, they are dangerous because of their unpredictability and invisibility. If a rogue planet were to pass through our solar system, it could disrupt gravitational balances, destabilizing orbits and increasing asteroid activity. In extreme cases, it could even lead to catastrophic collisions. A planet-sized object appearing without warning is not just unlikely, it's one of the most silent and unpredictable cosmic threats imaginable. Neutron stars. Neutron stars are formed when massive stars collapse after a supernova, but don't become black holes. What remains is an incredibly dense core made almost entirely of neutrons. These objects pack more mass than the Sun into a sphere only about 20 kilometers wide. The density is so extreme that a single teaspoon of neutron star material would weigh billions of tons. Neutron stars often spin rapidly, sometimes hundreds of times per second. As they rotate, they emit beams of radiation from their magnetic poles. If these beams sweep past Earth, they can be detected as pulsars. The radiation from a neutron star can be incredibly powerful. At close distances, it could strip away atmospheres and sterilize entire planets. Their gravity is also extremely strong. Anything that gets too close would be crushed and compressed beyond recognition. When two neutron stars collide, they create one of the most energetic events in the universe. These collisions generate gravitational waves and produce heavy elements like gold and platinum. Despite their small size, neutron stars are among the most dangerous objects in existence, combining extreme density, rapid rotation, and intense radiation. Magnetars. Magnetars are a special and extremely rare type of neutron star, with magnetic fields far stronger than anything else known in the universe. These magnetic fields are trillions of times more powerful than Earth's, making them the most magnetic objects ever discovered. The effects of such an intense field are almost impossible to fully imagine. At relatively close distances, a magnetar could disrupt electronic systems instantly, wiping out satellites, communication networks, and any form of technology. At even closer ranges, the effects become far more extreme, going beyond technology and directly affecting matter itself. The magnetic force is so strong that it can alter the structure of atoms. Electrons could be pulled away from their nuclei, effectively breaking down matter at a fundamental level. In such an environment, the very building blocks of reality begin to behave differently. Magnetars are also highly unstable. They experience what scientists call starquakes, sudden and violent shifts in their solid crust. These events release enormous bursts of energy in the form of gamma rays and X-rays, some of the most energetic forms of radiation in the universe. Even from across the galaxy, these bursts can be detected, and in rare cases, they can briefly affect Earth's atmosphere, causing measurable disturbances despite the immense distance. If a magnetar were significantly closer to our solar system, its radiation and magnetic influence could pose serious risks to life, potentially damaging the atmosphere and exposing the surface to harmful radiation. What makes magnetars especially frightening is that they are relatively small, difficult to detect at large distances, and incredibly powerful at the same time. They combine invisibility with extreme destructive potential. They represent one of the most extreme and dangerous expressions of physics in the universe, where the normal rules of matter and energy are pushed to their absolute limits. Alien megastructures. Some of the most intriguing and unsettling cosmic mysteries involve objects that might not be natural at all. Instead of being formed by known physical processes, these phenomena raise the possibility of something artificial on a truly astronomical scale. Astronomers have observed stars with unusual patterns of dimming that don't match typical explanations like orbiting planets, asteroid fields, or clouds of dust. In some cases, the light from a star drops in irregular and unpredictable ways, suggesting that something large and complex could be partially blocking it. This has led to speculation about alien megastructures, massive constructions potentially built by advanced civilizations to harness energy on a scale far beyond anything humanity could currently achieve. These structures would not just be technological achievements, but signs of civilizations operating at levels we can barely imagine. One of the most well-known concepts is the Dyson sphere, a hypothetical structure that could surround a star and capture a significant portion of its energy output. Instead of relying on a single planet, a civilization could use this energy to power entire networks of habitats, machines, or even interstellar systems. If such structures exist, they would represent technology far beyond our current understanding of engineering, materials, and energy use. Even detecting one would fundamentally change our understanding of life in the universe. While most unusual observations can still be explained by natural phenomena, the idea remains scientifically fascinating. If a civilization could build something on that scale, it would have access to almost unimaginable energy resources, potentially allowing it to reshape entire star systems. This raises profound questions about the limits of technology, the evolution of intelligence, and the possible existence of civilizations far more advanced than our own. Even without confirmed evidence, the possibility alone adds a powerful sense of mystery and uncertainty to our understanding of the universe. The Great Attractor. The Great Attractor is one of the most mysterious gravitational anomalies ever discovered. It lies in a region of space known as the zone of avoidance, an area heavily obscured by dust and gas from our own galaxy, which makes direct observation extremely difficult. Despite this limitation, astronomers have been able to detect its presence through the motion of galaxies. When scientists map the movement of thousands of galaxies, they notice something strange. Instead of moving randomly, many of them, including the Milky Way, are drifting toward the same region of space. This motion suggests the presence of an enormous concentration of mass exerting a powerful gravitational pull. What exactly is causing this attraction is still not fully understood. It could be a massive cluster of galaxies or part of an even larger structure known as the Laniakea supercluster. Some estimates suggest that the mass involved is equivalent to tens of thousands of galaxies. The unsettling part is that we cannot clearly see it. We are being pulled toward something hidden, something we can only infer through indirect measurements. Over cosmic timescales, this movement will continue, slowly guiding our galaxy across the universe. It's not an immediate danger, but it's a reminder that even entire galaxies are not stationary. They are constantly being influenced by forces we can barely observe, moving toward destinations we do not fully understand. The Boötes Void. The Boötes Void is one of the largest known empty regions in the observable universe, and its scale is almost impossible to comprehend. It spans roughly 330 million light-years across and contains very few galaxies compared to what we would normally expect in a region of that size. To understand how strange this is, you need to picture the large-scale structure of the universe. Galaxies are not spread evenly. Instead, they form a vast cosmic web made of filaments and clusters, with empty spaces called voids in between. But even among these voids, the Boötes Void stands out as unusually large and unusually empty. If the Milky Way were located inside this void, the night sky would look drastically different. Instead of seeing countless galaxies in every direction, there would be long stretches of darkness with very little visible structure. The universe would appear far more isolated and empty. Scientists believe voids form as matter is pulled together by gravity elsewhere, leaving behind regions with very low density. However, the size of the Boötes Void pushes the limits of current models, raising questions about how such a vast empty space could develop. While it doesn't pose a direct threat, it represents something deeply unsettling. Regions of the universe where almost nothing exists. It's a reminder that on the largest scales, the universe is not just filled with matter. It is also defined by immense silent emptiness. Eridanus Supervoid. The Eridanus Supervoid is linked to one of the most puzzling and debated observations in modern cosmology, the cold spot in the cosmic microwave background. This region appears significantly colder than the surrounding areas, suggesting that something unusual is affecting the radiation traveling through that part of space in a way we don't fully understand. One leading explanation is that a massive void, far larger than typical cosmic voids, is responsible for this anomaly. As light passes through such an underdense region, it can gradually lose energy, creating a colder signature when observed from Earth. This effect, known as the integrated Sachs-Wolf effect, can influence how we perceive ancient radiation from the early universe and slightly distort our measurements of temperature. However, there's a problem. The temperature difference observed in the cold spot is stronger and more pronounced than what most theoretical models predict from a void alone. This has led scientists to question whether the Eridanus Supervoid is truly sufficient to explain the anomaly or if something else is contributing to the effect. Some researchers have explored alternative ideas, including the possibility of unknown physical processes, measurement inconsistencies, or even rare statistical anomalies that just happen to appear significant. More speculative theories go even further, suggesting potential interactions with regions beyond our observable universe, though these ideas remain highly controversial and unproven. What makes this particularly unsettling is that it directly challenges our understanding of how the universe evolved over time. The cosmic microwave background is one of the most important pieces of evidence we have about the early universe, and any unexplained irregularity forces us to reconsider existing models. The cold spot remains unresolved, making it one of the most intriguing, debated, and mysterious features ever observed in the cosmos. Phoenix A. At the center of this galaxy lies one of the most extreme objects ever proposed, a black hole so massive that it challenges the upper limits of what we once thought was physically possible. Estimates suggest that this black hole could have a mass of around 100 billion times that of the Sun, placing it among the largest and most extreme ever considered by scientists. However, measuring black hole mass at such enormous scales is incredibly difficult and filled with uncertainty. Scientists rely on indirect methods, such as observing the motion of surrounding gas, stars, and even entire galaxies, or analyzing the brightness and behavior of the accretion disk as matter spirals inward. These methods can introduce significant uncertainties, especially when dealing with objects located billions of light-years away. Despite these limitations, this black hole remains a strong candidate for one of the most massive black holes ever identified. Its sheer size raises important questions about how such an object could form, evolve, and continue growing over time. Black holes typically increase in mass by consuming nearby matter or merging with other black holes, but reaching this scale would require an almost unimaginable supply of material over vast cosmic timescales. If confirmed, it would suggest that black holes can grow far larger than previously expected, potentially reshaping our understanding of galaxy formation, large-scale structure, and the evolution of the universe itself. Even more unsettling is what such a black hole represents. It's not just large, it's an extreme example of gravity completely dominating everything around it. Entire regions of space can be controlled by its influence, bending light, distorting time, warping space itself and consuming anything that gets too close without any chance of escape. Dark matter and dark energy. Everything we see, stars, planets, galaxies, makes up only a small fraction of the universe. The vast majority is composed of dark matter and dark energy, two components that we cannot directly observe but that dominate the cosmos and define its large-scale structure. Dark matter acts as an invisible framework, holding galaxies together through its gravitational influence. Without it, galaxies would not have enough mass to stay intact, and stars would drift apart into empty space. Even though we cannot see dark matter directly, we can detect its presence through the way it bends light from distant objects and affects the motion and rotation of visible matter within galaxies. Dark energy, on the other hand, is even more mysterious and far less understood. It is responsible for the accelerated expansion of the universe. Instead of slowing down over time due to gravitational attraction, the universe is expanding faster and faster, driven by this unknown and invisible force pushing everything apart. Together, dark matter and dark energy make up about 95% of everything that exists. That means everything we understand. All visible matter, including stars, planets, and even ourselves, is only a tiny fraction of the full cosmic picture. What makes this truly unsettling is how little we actually know about them. We don't know what dark matter is made of, and we still don't fully understand the nature or origin of dark energy. They cannot be captured, observed directly, or easily explained with current physics models. In a way, the universe is dominated by invisible forces we barely comprehend, silently shaping everything around us. From the formation of galaxies to the ultimate fate of the entire cosmos. The universe isn't just vast. It's filled with forces beyond imagination, invisible, silent, and sometimes unstoppable. And the most terrifying part? We've only just begun to understand it. If you enjoyed this video, make sure to like and subscribe to the channel, because out there are still countless cosmic horrors waiting to be discovered.